In this video, we are going to be looking at Gauss's law again, but specifically at how the electric field is affected by various conductors or insulators, how charge distribution varies in those situations. All of this is trying to understand the electric field better. So you may or may not recognize this. I don't know if you've ever been to the Museum of Science in Boston, probably, and you may or may not have been to the lightning show. And if you have, you've seen something like this. And I'm just going to mute this because we don't really need to hear the audio on it. But this museum employee is doing a show and demonstrating and standing in there, and the lightning is striking the cage, right? And sort of the question is this actually a safe thing to do? Right? Of course, if you've seen the show, you know that it works. You can do this, and it's not the end of the world. So kind of we know the answer, but why? When it comes to conductors and insulators, there's differences about how the charge works and how the electric field works. So for insulators, the story is simple, right? The basic idea is that you put charge somewhere and it stays put. Wherever it is, it's there. So if you put it on the surface, it stays on the surface. If you spread it out evenly or not so evenly in the middle throughout, then it stays there. So finding the amount of charge enclosed can be difficult because it might vary as you move through the object. You might have to do an integral with regards to what the charge distribution is. So that's insulators. Think of a piece of cloth, a piece of plastic, your sweater that gets charged up on a dry day, that kind of thing. Conductors, on the other hand, it's not as simple, but in many ways it's more predictable. So the charge can move around, right? And so this is an interesting little picture here. It has to move if there is an electric field, because electric fields apply forces to charges, right? Like there's nothing you can do about that. So if there is an electric field, the charge will move. If F net equals 0, then it doesn't have to. Or this should really say F net is not equal to 0. But if F net is 0, it won't move, right? If there's no electric field, the net force will be 0, and then it will, stay put. So it will move until that condition is met, right? And it reaches this equilibrium. Where exactly does it go, and how does it arrange itself? And that's really what we're going to be looking at. So take an arbitrarily shaped object, put some positive charge on it. Well, initially, you might be able to get the charge to do this in a conductor, but the charge is going to try to get away from itself as much as possible, and it will flow around and move until it reaches electrostatic equilibrium. And that means there must be 0 electric field inside the conductor. So if we draw a Gaussian surface right inside, if there is 0 electric field inside, what does that tell us about the distribution of charge? Well, the electric field, dA, the flux, must be 0 if there's 0 charge enclosed. And if we know there's no electric field, then the only other variable there is that the charge enclosed must be 0. So that means the only place for the charge to be is on the outside of the conductor. It has to be on the surface. And this is, if there's nothing else you remember fully from this video, it's that when you have a conductor and it has an excess of charge, the charge will move around, and we'll do it very quickly, so you probably won't even notice. And then the charge will be distributed as far away as it can be from each other on the surface of the conductor. So here's kind of our summary of this, that excess charge quickly moves around until we get to this point where there's 0 electric field inside the conductor, and that can only happen if all the charge is on the outside. It doesn't matter if it's a shell or a sphere. It can be a really strange shape. You could have external charges, or even if you put a conductor inside of an electric field, that will push charge around and then until this condition is met. So lots of interesting stuff there. We can think about strangely shaped objects, right? If we have something that's kind of teardrop shaped, well, the part that's kind of spherical has a pretty spread out distribution, but as it gets toward a point, more of it will go there, which is kind of an interesting idea. The electric field will still be 0 inside. If you have a sphere completely uncharged and you place it inside of a uniform electric field, well, the electric field wants to push positive charge one way and negative charge the other way, so it will separate. And it will do so that there's no electric field inside. And then you can do this with any arbitrarily shaped object. If you place a positive charge somewhere in space and place some conductors, this cube, an irregular shaped thing, one that looks kind of like a potato and sort of L-shaped. But what will happen is the charge will flow around inside of it until the electric field is zero inside. And the stranger the shape, the less easy it is to say exactly where the charge is, but you can generally say that, oh, the negative will move toward the positive, and the far side away from the positive will be left as a net positive. So insulators, conductors, right? You can put the same amount of charge on an insulator and spread it evenly throughout. This is usually our example. It has some volume charge density. With a sphere, if you put some charge on it, a spherical conductor, it will be on the outside. And so it has a surface charge density, right? For a cylinder, right, you can spread it out evenly. For a conductor, it's all on the outside. For a plane, right, if you have a plane and you're kind of looking at the side of it, a plate of charge, you can distribute it if it's made of, styrofoam or plastic or wood or something like that. But if it's made of metal, all the charge will go to the outside. Any random shape. The rho could be constant throughout it if you wanted to with an insulator. But with a conductor, the surface charge density probably won't be uniform because it needs to spread out to meet that condition of zero electric field inside. Right? So what? What do we do with all of this information? Well, the potato-shaped objects aren't really that interesting to think about. What is interesting to think about is let's take a conducting sphere with a particular amount of charge on its surface, right? Which we know is where the charge will go if you put charge on it. And then we surround it with an uncharged conducting shell. All right. Now, the exact way to do this isn't maybe obvious, and what we call this, it's a capacitor. Get there. What's going to happen? Well, if there is a positive charge on the interior, there's of course going to be an electric field from it, right? But we know that inside of the metal, the conducting shell, it has to be zero electric field. And so what we can do is we can create a Gaussian surface inside the shell, like this, and say, well, how is it that there's a positive charge, unbalanced positive charge right in the middle of the whole thing? There should be electric field lines pointing outward, but there is zero electric field inside that shell. Well, in order to do that, we need to think about the flux, right? Must be zero to get zero electric field. That's our formula, right? E dot dA is zero. But then how do you make that zero? You have to enclose zero charge. So how do we enclose zero charge? We've clearly enclosed positive charge right now. Well, the only way to do that would be for charge in that conducting sphere to move around relative to what's going on. And so we end up with negative charge moving into the center in an equal amount to what was on the positively charged sphere in the middle. So now my dotted line, my Gaussian surface, encloses a positive Q from the charged object in the middle and the negative Q that has moved to the inside surface of that sphere or shell. And then, because that's a neutral shell, we didn't add any charge to it. If negative Q went to the inside, then the outside must be positive Q. You might say, but isn't that a charge differential? Wouldn't we have an electric field? Yes, but that electric field generated by that charge separation, plus the electric field going outward from the inside charged object, will add up to zero inside the shell. And Gauss's law helps us show that this has to be true, because anytime you enclose zero net charge, you have zero electric field or zero flux. So let's do another example. This time, I have a solid conducting sphere with a positive Q in the middle, and then I put around it a conducting sphere that is negatively charged at negative 2Q. So unlike the previous example where the shell was neutral, this one has to maintain a net charge of negative 2Q. So what needs to happen? Well, we know that inside the conductor, there still needs to be zero electric field, right? That's our criteria. So we draw that Gaussian surface dotted line. We know that Gauss's law says that that needs to be zero and that we need to have no net charge. That means the inside surface needs to be a negative Q in order for that to enclose zero charge. And that means the outer surface has to be a negative Q as well, so that the total amount of charge on this shell is negative 2q, right? We can't change that. We didn't give it that charge anywhere to go. All we've done is force it to move around so that we can maintain what we know is true, which is that there's always going to be charge distributions that provide zero electric field inside of a conductor. Another example. Here we've got a shell with kind of a thicker radius like this, right? A more, instead of just a thin shell. We have two different radii, and it has positive 10 coulombs of charge. Where is that charge? Well, it has to be on the surface, right? That's how it works. Because if you enclose any of that charge with a Gaussian surface inside of there, then we would have an electric field, so that doesn't work. Now we put a point charge of negative 15 coulombs right in the center of the shell. Okay. What happens to the charges on the shell? Well, the shell then is going to have its charge move around because that negative 15 we need to have some positive on the inner surface so that when you draw your Gaussian surface, right, we can have negative 15 coulombs there, positive 15 coulombs there, negative 15 coulombs at the center so that we're enclosing zero, so we can have zero electric field. And now the outer surface must be negative 5 because positive 15 plus negative 5 gives us the positive 10, which is our net charge on that shell. And we've distributed it in such a way that we can enclose zero when we have a Gaussian surface that is inside the shell. Another example, positive 7q, negative 2q. Right? The inner surface of the shell must have the same amount of charge, but in opposite as that, so it has to be a negative 7q. But if there's a negative 7q and the net charge on the shell is positive 7, is negative 2, we need a positive 5 added to that negative 7 to get negative q in total. Another example. This time, though, it's not a sphere. This is a rod. This is what we call coaxial. So there's one axis running into and out of the screen, and then there's a long wire in the middle. We call it a conducting rod. The radius r and some linear charge density, negative. Then there is a gap of air, and then there's a cylindrical conductor around it. And so if you've ever looked at the wire that cable television, satellite television comes into, it's usually a plastic wrapped, often black or white, or sometimes the color of the wall to blend in, that kind of thing. But if you were to cut it, you would see in the middle is a wire. Then there's an insulator, usually kind of foam kind of thing. And then there's a wrapping of basically foil in a lot of cases, or sometimes braided metal, woven metal around it to be that outer conductor. And so basically this is what you have. You have a coaxial cable. There's reasons for this, and we'll talk about that more when we get into them as capacitors. But suffice it to say, this is a very real world example. And so what we have is a linear charge density of positive on the outer shell and of negative on the inner, rod. And if we were to cut it away, this would be kind of what it looks like, right, in a force perspective. So what are the locations and magnitudes of all the charge? So we have in microcoulombs per meter here. And so we don't need to actually convert this to absolute amounts of charge. We can just keep it in terms of charge densities. If we draw our Gaussian surface, we know that by definition, there needs to be no electric field inside of a conductor. So that means the amount of charge enclosed by that Gaussian surface has to be 0. Well, if we have negative 3 microcoulombs, right, on the rod per meter, then if this Gaussian surface encloses, say, a meter of the coaxial cable, then it would enclose negative 3 microcoulombs of charge inside, which means we need a positive 3 microcoulombs of charge on the inner surface per meter. And then we know for the outer surface, the outer cylinder, the outer pipe as we've called it, right, has a total of positive 5 microcoulombs. And now we know that positive 3 microcoulombs per meter are on the inner surface, which means we need 2 microcoulombs per meter on the outer surface. Right? So what does the electric field look like now that we've got this? Well, we know there's no electric field inside. That's the easy one. Either of these conductors, right? And we know that electric field goes from positive to negative. So inside that gap, which in this case is air, but could be foam or anything, paper, sometimes with these kinds of things. And then on the outside, we know that lines of electric field go from positive charge out to infinity. So this is what the electric field looks like for this example. Kind of interesting. So we've got sort of four regions. We've got one, which is the center of a conducting rod, which has to have zero electric field. Two, which is between two different conductors with opposite charges. And so we have electric field pointing inward. Three, where again, zero electric field because it's inside of a conductor. And four, outside of, once you're outside, you could just think of it as a cylinder with a net charge of, positive 2 microcoulombs per meter. So we want to think of this in another way. Can we graph these regions? Well, we already know the electric field in the inside of the conductors. So that one's pretty easy, right? In region 1 and 2, or 1 and 3, excuse me, inside the conducting rod and inside the conducting shell, zero electric field. The next region would be region 2, where you're between the inner and outer, the radius of the inner object and the inner radius of the outer object. And so we can create a Gaussian cylinder there. How much charge do we enclose? Well, it's lambda times L, and lambda was that amount of negative charge. The lateral surface area is 2 pi r times L. We don't worry about the end caps because all of this is radial direction electric field. So the end caps with their out of the page and into the page aren't going to count for area. And we can simplify this down to electric field is stuff, a charge density over constants times 1 over r. So we get a radial relationship, a 1 over r relationship, where you get weaker as you go further out. We know that lambda for the rod was negative 3 microcoulombs per meter, and we can actually calculate what this would be right at the inner surface, right? Obviously, because this depends on little r, there's a range of electric field strengths as you go from object 1 to object, or from surface 1 to through region 2 out to surface 3. So we can fill that one in. This is the electric field here. It's negative. Why is it negative? Because it's pointing radially inward instead of outward. It's the opposite direction that a positive electric field would be. So that's why we put it there. Then we go to the outer region. You can draw a Gaussian surface outside. This is the easiest one. This is the one we could have done via Coulomb's law if we wanted to, almost. It's for a cylinder, so we can't exactly. But we just add up all of the charge. So the Q enclosed is just lambda times L. And lambda in this case, in net, is plus 2 microcoulombs per meter. And right at the edge, 3r, it's going to be 1.2 times 10 to the 5th, and then it's going to go off down like 1 over r. This is now a positive electric field because it's radially outward. And we can fill in our last section a 1 over r relationship. So my graph is not perfect here, but these are 1 over r relationships in regions 2 and 4, and 0 electric field in regions 1 and 3. So the last idea is this idea of the Faraday cage. And this is an incredibly dramatic looking thing, but you have this coil Faraday style generator that's generating electrostatic charge, and it's got this person inside of a cage, a literal cage. But anything that is a conducting material can be a Faraday cage as long as it is fully enclosed. You notice that this has gaps, but the way it works, things will go in there. It blocks all external electric fields because when you're inside of it, the electric field needs to be 0. So the charge will move around in the metal to make this work. This actually means that if you took a radio, right, and even your cell phone, right, which uses radio frequency, and you go inside a Faraday cage, you can completely block the signal. Now, the exact spacing matters. For this kind of stuff, all you really need is, something like that. But if you're talking about radio signals, you have to think about the wavelength there. That's a whole other issue. It cannot block magnetic fields, though. This only blocks electric fields, which is interesting. We'll talk more about magnetic fields in a bit. They can protect you in an electrical storm, though, right? If your car gets struck by lightning or the plane you're in gets struck by lightning, the first one, cars getting struck by lightning, not that common. Planes getting struck by lightning, pretty common, right? As it turns out. But it's fine because the whole shell is metal. It's a conductor. It's a Faraday cage. All the electronics inside are going to be just fine. There you go. So we'll continue our discussion about electricity and magnetism as we go, but that's how we look at the electric field and some of the really interesting applications of it using Gauss's law.